Yes, well, hello everyone. Thank you for coming in this nice weather. My name is Oleg. I'm a systems architect at ICOS Carbon Portal. More about what it is later. And I used to work for a long time at Capish before. And Capish works with ontologies as well, which are the main topic of my talk, and also metadata and how they are applied and used to publish scientific data about greenhouse gases and global warming and so on. First of all, the main organization that I represent currently, called ICOS, it is an abbreviation for Integrated Carbon Observation System. It is a large European research infrastructure which collects scientific data on carbon cycle and greenhouse gas budget, or basically greenhouse gases such as carbon dioxide, monoxide, methane, uh, and um, and then the activity is split into three themes: atmosphere, ecosystem, and ocean. And well, this is a map showing most of the stations in the network. And so the blue one are the ocean. Some of them are mobile, these are ships, and then the red ones atmosphere, green the ecosystem, and the yellow are mixed atmospheric ecosystem stations. Well, the total number is about 120. So this is just a photo for you to reflect a little bit on the diversity of the ecosystems and the nature in Europe. And this is, of course, the sites locations where the stations are. Now, more specifically, what Carbon Portal is and why this is interesting for IT focused full cafe is because we are sort of an IT department for this big project, you could say. The main role is a so-called one-stop shop for the data. So that means that we are making sure that the data is findable, available, downloadable, and so on. We are hosted by Lund University and co-located and based at the Department of Physical Geography and Ecosystem Science, as it is called. That's where we sit, GeoSent 2 in Lund. And well, what we do more specifically is we ensure that there are technical means of uploading the scientific data to us. That's not for end users, these are for our collaborators. Then we provide a search interface to locate all the data objects and offer some visualizations, and then take care of metadata, the main topic for today's talk, and also the key to most of the services. And then we allow users actually to send us queries of their own choice about the metadata. And then we do also a service of minting permanent identifiers, PIDs. Well, those are things that are well known in the academic world. Actually, maybe I can show you an example. So an example of a permanent of a PID would be this one. This is the address of the talk, and this whole URL is actually an pretty ancient URL shortener by the internet standards. This is something that the scientific community has been using since long time ago. It's actually based on an internet protocol called Handle system. Well, anyway. Basically we create one such permanent identifier for every data object just to make it referable in scientific publications. And then we make different other services which are not very related to metadata, so we will not talk about those. But for most of the key services, for all of the core services, metadata is really the key, because it describes all the main actors in the infrastructure. So the stations people, their roles, instruments, how the data is collected, and then the data objects themselves and their provenance, that is the story, the history of their acquisition, processing and submission, and so on. So this is really the key to enable all the services. And maybe actually just not to limit things to the slides, we can take a quick look at the search interface just to get an idea about it. What is it that is driven by the metadata? So well, here we have a multifaceted search where it is targeted mostly at scientists, those who want to find the data and then maybe perform some modeling or analysis and produce some scientific reports and articles. And well, so this is a multifaceted search interface where people with different, well, can start looking at searching the data from different viewpoints. For example, one could pick a theme and say, well, I actually am interested in atmospheric data, and the list is filtered, and then well, you can be interested in actually a certain, maybe a measurement. You could say I want to find gas mole fraction, and then maybe you happen to know where it is from. Well, and just for this example, I happen to know. Let's pick a station. I will show you why it is interesting in a minute. And well, let's pick the largest data set, and we can look at the data. Well, the metadata here is, for this particular one, is not very detailed, but well, what is interesting about this data set is that it is one of the most maybe well, obvious. It's a curve that demonstrates one in the most obvious way the effects of the human activity on the state of the atmosphere. So these are pretty long-term measurements, as you see, from 1974 and up to now. Well, the data set is not quite modern, but well, here you see these. So each wave here is actually 1 year, and you see these are the seasonal variations, and the concentration of the carbon dioxide grows. So these are parts, so-called parts per million, and you see the number. Just in these last 40 years. The change has been quite substantial. So from 330 to 400, that's a big change on a planetary scale. And well, so that's what is special about this station is actually it is located on Hawaii, far away from civilization, and so the signal is pretty clean. It's unaffected by industry and artificial sources of CO2. So it's kind of a reference source for the average situation on the planet, so to speak. Yes, well, let's go. How do I go back? Yeah, I want to like this. No. Oh, yes, this was this. Yeah, so that was just one example, just not to bore you with the slides and the text, and but it is driven. The interface is completely driven by the metadata, of course, and well, now it's time to explain the principles and approaches that we have taken to publishing the metadata on the web. And this was, of course, by no means a new problem. So we used a set of standard technologies that exist and in principles that have been formulated for the web, and they are called linked data principles. And there is a stack of standards called semantic web, which we try to follow. And well, what the semantic web is, well, it is a bit of a convoluted term. It is simultaneously the number of technologies for publishing the metadata or data in the machine understandable form. It's also you could say a vision in a way, where most of the websites publish some of the metadata in this fashion, and then of course the data and services themselves. Then the standards, they come from World Wide Web Consortium. This is the same authority that standardizes things like HTML and XML. Well, the main keywords or technologies which are relevant would be RDF, that's the data model. Sparkle is the query language, analogous to the SQL for relational databases, and all that is the language for expressing ontologies. And it's mostly, all of this is targeted not at end users, it's rather at information architects and the developers. So this is something that works behind the scenes. One very important motto for this approach is the web is your database. Which is related to this among other things, to this query language and the services that one publishes. So one exposes the possibility to send queries to the third parties, sort of like an API, but where the query is unrestricted. A few basic, very simple ideas. So the key idea number one is that everything that you want to mention in your metadata, it gets identified by URI or URL, which is a globally unique ID by design. And this URL should also be referenceable, which means if you put it in your web browser, your browser will open a web page about this thing that you refer to with this URL. Or if you open it not a web browser, but some different HTTP-aware agent, you may get a different format, not an HTML page, but something else, maybe XML or JSON, something machine readable. Then about this data model is also extremely simple. It just prescribes to formulate everything as a sequence of simple statements consisting of 3 components called triples. And so the components are called subject, predicate, and object. And it's basically a human sentence, if you like. So if you have one URL representing yourself, then you can have another URL representing a notion of a name or having a name, and then you could have a string. So that would be your name is something, very simple, or age. Or you could have an environmental research station, and then a predicate representing a latitude and longitude, and then a literal representing the coordinates, and a double floating point number. And so that's pretty much it. So it's a sequence of simplest statements of a human language, if you like. So these ones, they can be literals or URLs, and these two, they have to be URLs. And then, well, of course, one statement, well, it can have one statement's object can be a subject of another statement, which means that you can chain them together and spread out So effectively, this data model becomes what is called directed labeled graph. So it's like a network. It's a graph. That's what the difference distinguishes it from tables of the relational databases. Well, it's just a slide to summarize the structure of an RDF triple. So 3 components. Well, all the 3 can be URLs, and but the third one, the object, can be literal, because when you have a graph, well, it has to terminate sometimes. Well, it so happens that actually there is quite some metadata published in this fashion online already, and this service keeps track of different data sets that are published, let me see if I can. Yes. So they come from different knowledge domains. As you see, it's mostly life sciences and governments. So public sector, pretty much, I would guess, some linguistics, and then some cross-domain. For example, all of formal information. Well, you cannot read it here, of course, but this is DBpedia. That is a metadata extract from Wikipedia. So basically, info boxes that are available on every Wikipedia page, they exist in the form of RDF. Published and queryable with Sparkle endpoints and so on. Yes. Then one interesting property. So since an RDF is basically a sequence of simple statements, what it implies is that you can merge 2 different databases in a trivial fashion. It is just a simple concatenation. So every RDF is just a table of a fixed schema. You have 3 columns always only. So merging 2 databases is just appending one sequence to another. This is, of course, quite different from the relational database world. And then the databases who have RDF as their native data format, they are called triple stores. And well, one extra feature that they usually have is that they group the triples into so-called graphs. Well, it is kind of like an annotation of a subset of triples with an extra URL. It is quite useful because sometimes you want to scope your triples. So you don't want to have just a flat list. You want to have some structure sometimes. So this is a form of a container. We'll see practical why this is useful a bit later. So this was the data model for the metadata and how it's supposed to be published online. And well, then now there is just one last push to digest that remains, and that is the ontology. So what it is, and well, the term comes originally from philosophy, and it is, well, as the text tells us, is just the study of the nature of being and becoming. Well, being, existence, reality, and the basic categories. So it is actually not completely unrelated to the notion of ontology in computer science, because it is, well, yeah, there are many ways to formulate what it is. Like one is the text that you can see here, but a simple thing to remember, or a simple way, not very strict one, would be to say that this is a formalized knowledge. You could, I think one could put it like that. It's much easier to remember. It's a formalized knowledge in some knowledge domain, of course, not all human knowledge, but just some part of it, some area. Or as they call it, domain of discourse, or knowledge domain, some area. Well, and then, well, of course, one needs to be able to the ontology itself, it needs to be somehow expressed. So one is a language for that, and well, the language that is endorsed by World Wide Web Consortium is called OWL. That's a scrambled acronym of Web Ontology Language. And well, it has the what one would expect there, notions of classes, subclasses, properties, subproperties, ranges and domains for the properties, and different restrictions, and the class expressions, all kinds of constraints. And then it has the notion of inference, like if something is a subclass of another, and it has another subclass, so then well, and the third one is the subclass of the first, and well, many many different things that are kind of can be naturally inferred from axioms, as they are called. We will not dig deep into this right now, because this is just a general introduction. Well, I think for the purpose of this talk is enough to we could think of this language a little bit like object-oriented programming. It's not really exactly that, but very roughly it is. There is some open source tooling available for inspecting and editing ontologies of this language. I will show you just a few. So there is one. So this one called protease, it is open source, and there are, well, just some screenshots. Don't need really to understand a lot, just to give you a feeling. So this is a class hierarchy that we have designed so far. It basically describes different notions that we are dealing with. And this is a list of properties that or relationships that exist between them. Well, nothing out of the ordinary. So just different notions are related. For example, like this is next version of it, it can relate to data objects. So data objects, they can come in versions, and so they can deprecate each other and so on. And then there are also different there is a different kind of properties. So these are called object properties because they relate the notions, and so these are called the data properties because they relate some objects or instances, if you like, and concrete values, so literals. For example, latitude to longitude, the coordinates, they have a value of a number. So the values, they come from XML schema data types. Well, that is basically it about the ontologies. And well, now I thought we can take a look a little bit about different examples of our services, and but in the not just blind walkthrough, but with a little bit of a context. So if we go back for a second to this slide, where I talked about graphs, the notion of graphs, like extra structure, extra containers inside of a triple store, just a way to group the sets of triples together. So we can look at the application of this now. So this is well, let's focus first on the reason why they are useful is that when querying a triple store, you can actually select which graphs you are interested in. So your query, it can be global. You can ask question, well, about every single statement that you have should participate in answering me. Or alternatively, you could say, I'm only interested in answers coming from the facts in this and that graph. So the good metaphor to this is the old overhead projectors and transparencies. You know, there used to be these plastic transparent slides that you would put on overhead. But what you could do, actually, you could stack them together. You could take a few and have pictures that would complement each other. So when you stack, you get a more potentially more rich picture, and then you can pick. So picking the graphs is essentially that. So here what we can do now is just we shall look at the examples of different things we have in production, and how they use different stacks, how they see. So of course, so in the end we have all of these in our triple store, but every application uses only a certain stack. So if we start from the very first thing that needs to happen in our infrastructure is that a station needs to be added to the list. So if a new station is created, it needs to be added to the list. So we need a metadata entry application where people who are responsible for this would provide us with the so-called provisional stations. So we need a schema for this, or ontology. And then we need that would be sitting in one RDF graph, and then we need another graph for these stations, and then we need an application that would populate this graph with some statements or facts. So well, it is very basic, but it does the job. This is what we have. So basically, everything one needs is to have something where one adds people, and then adds new stations and says who is the responsible for the station and some metadata. So in this case, well, we have some, well, it's nothing out of the ordinary. What is a little bit out of the ordinary is that this interface is actually completely generic. What it means is that the code behind it has no idea about atmospheric stations or ecosystem stations or principal investigators or all of this. So these are all strings you see and classes, or types. They come from the ontologies, and the interface itself is actually driven by it. So the interface is built on the fly from this one. Then, well, when this stack is populated, then we have another application that does. Well, it is actually not super exciting, but it was an important formal process. So different responsible people need to come in and submit some information about the station. It's just, well, you could say it is a bureaucratic procedure a little bit, but it needed the knowledge inside of this, and thanks. Everyone woke up. Yes, so that's yes, even before, yeah, well, I can show this one a little bit quickly. So there isn't really very much to it, but we can look, if you want, we can look at the picture of a station that is close, at some photos from the station that is closest to us. It is 60 kilometers north, or maybe 80 from Malmo. It's called Hiltemosse, and so as part of the procedure, they are supposed to upload some photos. Well, this is a forest in Skåne. Yeah, well, maybe you can take a look at a little bit of an glimpses of yeah, I don't know, you don't need to see so much of equipment. Well, never mind. The point here is that, well, this app, it is actually, when it operates, it sends queries to the triple store, and then it says, well, okay, I'm interested in these three layers, in the stack of these three graphs. And there is another one, for example, this map that you saw as a background picture on one of the slides is actually a live thing that you can explore, and it is also it is deployed well, on some you could say it is a random website. So it could be anywhere in the world, in fact. And still, what it does, it sends the query to our triple story in the background and fetches the metadata about the stations. So this is this motto: the web is your database in action. The key here is that anyone could do it. Anyone could write a visual application, a web page that would send things, send the query, and the query is absolutely arbitrary, no limit. It's actually a Turing complete language, I think, even. Well, not that you would want that necessarily, but it's absolutely any query that you can think of. Yes, then, well, what happens after this provisional information is entered is that there is some transformation process, which is also done using the Sparkle query language, in fact, but we will not look into that very much. And then it creates from this provisional information, it creates a certain view of the station. So it creates, things go to a different RDF graph, and which represents them using a different ontology. So this is, you could say, this process is what they call ontology alignment. Sometimes, well, this is a simple version of it, I would guess. But after that, we need to add some more metadata. We need to start describing what kind of data objects we expect. So we need another app to populate to enter more metadata. And then, well, what we have, I guess you could guess that it will look exactly like the previous metadata entry application, the same generic code, but now it is driven by different ontology. Yes, so different aspects of the data objects that you expect to upload can be entered here. For example, here we have the kinds of measurements that are performed, like you see here: air temperature, air pressure, and so on. And then we have a different data sets that have some columns and so on. So it's like a detailed level description of different data objects that we expect. So this is something one needs to have. And then this application, then it has the view, it sees these three layers, and this layer actually drives the interface. And then when the upload is performed, then this fourth level is populated, and then the search application that we have looked at previously, this one, it then sees all the four layers. So and because it needs all of it. It needs the information about the metadata. It needs about the information, the metadata about data objects themselves, and about stations and the ontology, all of it. So they're all necessary. Then another example of the flexibility of this approach with stacks is that we actually, except of ICOS, this big infrastructure, we now have a different you could say customer, I guess, if it is applicable in the public sector. So this is a Swedish national ecosystem network infrastructure called sites. Something seems to be happening with the projector, I think. We have but because the activities that they perform are so similar, we could actually reuse the same ontology that we had for ICOS, but just have a different graph that would have sites related metadata. And then there is, of course, there is a third metadata entry application, which again looks exactly the same, you could think, but in fact it's a different it's a different one. It populates different graph, and everything here is different, and it is scoped and separated. And then what this enables us to do is to have next to ICOS data portal, to have a sites data portal, which is an application viewing these three layers and well, it is styled differently, but it is the same software which is driving it. Well, it's just in the beginning, so there isn't a lot to show. Well, there is just only one data set. This is the weather data from, for example, temperature for 3 years. I think it's a 10 minutes temperature for 3 years, 150,000 data points, I think. Well, that's well, it's not really related to metadata as such, but what is related is that we have these the ability to scope with different graphs our applications. And well, this application, even though it is styled differently, and but it's exactly the same code. The difference is the choice of the layers, the choice of the transparencies for the stack. And then now the final thing, the final service that is maybe worth to show is so that these ones were more or less user facing so far, well, except of metadata entry, they are for technical users. But then there is this, this query endpoint that is available to everyone. We have a semi-user-friendly interface for that, where you can write a query or pick one of the several existing ones, like, well, I don't know, table of stations. Yeah, there is a prepared query, and that, well, you can run and you get some information in a tabular form. Well, and the point is that you can write any query and get answer specifically to your question that you want. And of course, this is just for testing, and the way you do it is that you put it into, you run it as an Ajax request from a web page, or you run it from a script if you want. For example, if you want to download a lot of data objects, that is what you do. Yes, we are almost there. Well, then I had a few of examples of the concrete ontology designs, but they are, well, they are just design patterns. They are not really they're not really related to the data model, to RDF, or to the query language, or to ontologies as such, because this kind of a design one could do in any well, in a relational database as well. But well, this is just to show some examples. So the design is actually not that different. You just draw some diagrams and see how different things are coupled together. So we have every data object has a specification which has a few attributes, and then it has a dataset specification which has a number of columns, and columns, the content of the columns is described, both technical content, so what is the value format, is it int or float, or is it 32 bits or 64 bits, or value type, that's the domain specific thing, what kind of measurements, is it a temperature, or is it well, I don't know, is it well, perhaps a humidity or photosynthetic radiation or something like that. And well, each of them, well, we introduced a notion. Well, we didn't really introduce it, but is coupled to a notion of a quantity kind, which is well, maybe it's best to show an example. These are very simple, basic things from basic physics, like angle or energy flux or length or portion or pressure or temperature, so that even if you don't have the domain knowledge, so you don't know these, for example, incoming shortwave radiation, well, it's hard to know what it is unless you are in the domain, but you can from this quantity kind, you can see that, well, it is actually energy flux, and then you see a unit, it is watts per square meter. and that's pretty much, that is what Sun is giving us. So that's easy. It makes it much easier to understand. So that's one of the purposes of the ontologies. They explain the meaning of the notions. So if you even so you can learn. So it is except of being able to drive some software, some generically written software, they also have this purpose of actually explaining things. Well, I think that will do. We have a couple of other examples about this provenance and how it is modeled. Basically, here we can only just say that we care about three things at the moment: when the data object was acquired, how it was produced if it was a result of a production, and when it was submitted, and its date, time, and who did it.